Hi everyone, welcome back to our Digital Systems video series. In this lesson, we're leveling up our study of Boolean Algebra by applying the Morgan's theorems to more complex expressions. I'll show you a step-by-step method to solve these without getting confused. So, let's briefly review the Morgan's theorems. The first theorem states that the complement of a product of variables is equal to the sum of the complement of each variable, okay? And the second theorem states that the complement of a sum of variables is equivalent to the product of the complements of each variable, okay? In other words, an AND operation is equivalent to an OR operation with complemented inputs, and an OR operation is equivalent to an AND operation with complemented inputs. In the previous lessons, we applied these theorems to expressions with 2 or 3 variables. Now the question is, how can we apply them to more complex Boolean expressions? Don't worry, it's actually quite simple and very easy to understand. Each variable in the Morgan's theorems can actually represent a more complex expression. For example, let's assume that x is equivalent to a times b plus c, and y is equal to a plus b times c. So now we can apply the Morgan's theorems using this format. So if x and y are equal to these expressions, we can write them like this. Now let's continue simplifying this expression. But before we jump into the examples, I want to teach you a very effective technique. I call it move the bar inside and switch the operation. It's simple. Whenever you have a long bar covering multiple variables, you break it and flip the sign. If it's a product, it becomes a sum, and vice versa. Now, before applying the Morgan's theorem, we must first identify the structure of the expression. Is it a sum or a product? In this case, we have a complement of a product, so we must apply the first De Morgan's theorem. Now, we apply De Morgan's theorems to the entire expression. That is, the product becomes a sum, and each term is complemented, like this. Okay? To continue simplifying this expression, we need to check if there are still complements applied to more than one variable. And as we can see, we still have these 2 bars covering the entire expressions, which means we can continue applying the Morgan's theorem. So applying the technique we discussed, move the bar inside and switch the operation, we obtain this expression. Notice that where we had a sum, okay, it becomes a product, as you can see, all right? Now, the question is, can we still apply De Morgan? Yes, we can, because we still have complements applied to expressions with more than one variables, here and here. So we apply De Morgan again to these terms, move the bar inside and switch the operation. And this leads us to the final expression. So remember, always check the structure before applying De Morgan. Now you might be wondering, why didn't we apply De Morgan's theorem to the entire expression at once, since everything was complemented? Well, we could do that, but I don't recommend it. As expressions become more complex, it's much safer to apply De Morgan step by step. By working in layers, you reduce the chance of making mistakes, and this will become even clearer in the next examples. Now, let's simplify this expression applying De Morgan's theorems. Remember, we must first identify the structure of the expression. Is it a sum or a product? We can think of this as a sum of 2 blocks. Let's call this first block x, okay? And this second block, let's call it y. In this case, we have a complement of a sum, all right? So we must apply the second De Morgan's theorem. Move the bar inside and switch the operation. So the expression becomes like this, okay? And as we can see, a sum becomes a product, and each term is inverted, where x is this block and y is this second block. The remaining terms stay the same. Remember, we're applying De Morgan's theorems in layers. We always start from the outermost bar and work our way inward. This means that the inner bars remain unchanged for now, as well as expressions under them, okay? Now, there's an important detail here. Notice that we have a double complement applied to this first block. Whenever this happens, we can apply the double negation rule. Rule 9 states that a variable with 2 complements is equal to the original variable. We proved this earlier in the lesson 3.2. So by canceling the double bar, we obtain this expression. Now let's continue. As we can see, we still have this outer bar apply it to all terms in the second block. So we apply the Morgan to this part only. Move the bar inside and switch the operation. Now notice that we have a complement applied to the expression e plus f negated. But in this case, we actually have a double complement. And there's an important condition here. The double negation rule can only be applied if both bars cover the entire expression, which is exactly what happens here. So we cancel the double complement, and this gives us the final expression, like this. So always pay attention to where the bar is applied. Now it's your turn. Pause the video and try to simplify this expression applying the Morgan's theorems. Alright, let's solve it together. First, we need to identify the structure of the expression. Here we have the complement of a product, okay? So we apply the first De Morgan theorem. Move the bar inside and switch the operation. The product becomes a sum and each term is complemented, like this. Okay? Now we continue simplifying. We'll still have a complement applied to a sum. So applying De Morgan again. Move the bar inside and switch the operation. The sum becomes a product and each variable is complemented. And this is the final simplified expression. Notice that we apply De Morgan step by step. Always work in layers, okay? Now let's move on to the second exercise. Pause the video and try to simplify this expression using De Morgan's theorems. Notice that we follow the same steps. First, identify the structure and then apply De Morgan's theorem. Alright, let's solve it together. First, we identify the structure of the expression. Here, we have a complement of a sum. So we apply the second De Morgan's theorem. Move the bar inside and switch the operation. In this new expression, the sum becomes a product, and each term is complemented. Now we continue simplifying each term. Again, we apply De Morgan. Move the bar inside and switch the operation. That is, each product becomes a sum, and each variable is complemented. Now, let's move on to the third exercise. Pause the video and try to simplify this expression using De Morgan's theorems. Alright, let's solve it together. Remember, first we have to identify the structure of the expression. Here, we have the complement of a sum with three terms, so we apply the second De Morgan's theorems for multiple variables. Let's use the same idea. Move the bar inside and switch the operation. The sum becomes a product and each term is complemented. Now we simplify each term separately. Again, we apply De Morgan. Move the bar inside and switch the operation. Each product becomes a sum and each variable is complemented. Notice that in this case, we have two variables, b and c, with double negation. So we cancel the double complement and the expression becomes like this, okay? Notice that the same rule works even for multiple terms. Always remember, identify the structure first, then apply De Morgan step by step. So in this lesson, we applied De Morgan's theorems to more complex Boolean expressions, learning how to identify the structure of an expression and simplify it step by step, working in layers. And most importantly, we follow the simple and consistent rule. Move the bar inside and switch the operation. At this point, we have completed our study of laws and rules of Boolean algebra. And these tools allow us to analyze, transform, and simplify logical expressions with confidence. By combining these laws and rules with De Morgan's theorems, we can handle even complex expressions in a clear and structured way. In the next lessons, we'll build on this foundation and start applying this concept to more advanced topics in digital systems. And keep practicing these techniques, because they are essential for logic design and circuit simplification. Thank you for watching, and I'll see you in the next lesson.